Hello, my name is Lawrence Bull, and I'm a research associate in the data-centric engineering program at the Alan Turing Institute. I'm also a member of the computational statistics and machine learning group at the University of Cambridge in the Department of Engineering. Today, I'm going to talk about modeling methods for digital twins of distributed fleets of engineering assets. To begin with, it's useful to consider why it is necessary to model engineering systems at the population level. And the main motivation is that we're able to share information between distinct machines or domains. Specifically in application domains such as asset management or performance and health monitoring, the data are incremental. That is to say that they arrive throughout the operational life of the monitored system, and large data sets are rarely available a priori that are useful to train our machine learning algorithms. There are systems with rich historic data which have been in operation for a long period of time, and also systems with very sparse or limited data sets. These could be turbines recently operational within a wind farm or trains within a transportation network, for example. The key idea is whether data-rich systems can support those with incomplete information or those that are recently in operation. Despite the increasing prevalence of engineering population data in many engineering applications and industries, the models that we use to represent these data and to make predictions remain system-specific. If instead we let our assets constitute a wider population, the value of their combined data is greatly extended. A popular paraphrase here is that the whole is greater than the sum of its constituent parts. The focus of this work is hopefully paving the way towards an interconnected ecosystem of digital twins. That is, multiple digital representations of physical infrastructure that allow for sharing of information and message passing between models. This aligns with UK government strategy, in particular that of a national digital twin. To motivate why sharing information might be useful in an engineering setting, we consider a truck fleet survival analysis for a simulated dataset. This study is in particular in collaboration with Maharshi from Cambridge, who will be at the workshop later in AI UK for any questions. Specifically in this setting, we're considering the prediction of hazard functions over a collected population of vehicles. This population contains different subfleets. Some might correspond to mining or forestry vehicles, others may correspond to retail vehicles. And we hope that by learning these hazard functions in a combined inference, we improve our prediction. The hazard is the instantaneous rate of failure of components within the truck fleet. This could include turbochargers or alternator components, for example. If we first focus by learning independent models, while we have good predictions in our data-rich domain, as our domains become more sparse, the accuracy is less representative of the underlying ground truth, shown by the black line, and the uncertainty appropriately grows for sparse domains. If we instead learn our models at the population level, and we allow for knowledge transfer either by shared parameters or correlated parameters, we can greatly improve our representation of the underlying hazard functions, and our uncertainty is appropriately reduced. Additionally, the variance of our interpretable parameters of our survival model is reduced. The data-rich domain has a relatively low variance reduction, while the data-sparse domains have a huge reduction in uncertainty as they leverage information from the data-rich domains. More information of this case study can be found on GitHub, which has the material for the workshop, which will be presented later in AI UK. Thank you very much for listening. If there are any questions, please feel free to get in touch via email. Thank you.